In this worksheet, we're given that a meter stick is hung from a string and it's balanced at the 50 centimeter mark, as we see right here. We want to calculate at what centimeter mark a 200-gram weight would need to be hung on the left side of the pivot to balance the following weights on the right side. Now, when doing this here, we have a formula that torque is the radius times the force. And when we're balancing things, we make the amount of torque on the left and the right the same. Kind of like a mobile, like a little child's mobile, where they have different items hanging from a bar. The thing to remember, though, is that the radius is always the distance from the center, or the more accurately, the fulcrum, from the center to where the object is located. So for this first one, we're going to hang the 200 grams at the 60 centimeter mark. And we want to know where should we place another 200 grams so that it's going to balance. So the first thing we're going to do is we're going to find the torque on the right-hand side. And the torque is the force times the radius. Now the force is the 200. That is the mass here, the 200 grams. The distance, the radius, remember, is the distance from the center to where it is located. So it is not 60 centimeters. Instead, it is 10 centimeters. It is the distance from the center, 50, to where the object is located. That gives us a torque on the right-hand side of 2,000. Now, we have to do is we have to make sure that we get a torque of 2,000 on the left-hand side as well. So to do that, again, we go to our formula. Torque is force times radius. It says we're always hanging a 200-gram weight on the left-hand side. And we want the torque to be the same as here, 2,000. So we have the torque. We solve for the other side to be 2,000. We're applying a force of 200 on the left-hand side, and we're going to solve for the radius. In order to solve, since it is multiplied to our variable, we divide to get rid of the 200. That gives us, with the radius on the left-hand side, of 10. So again, we need to be 10 centimeters from the center. That is not going to say we're going to hang it at the 10. We need to be 10 from the left-hand side of the center. So we're going to place our other 200 right here at the 40. For the next problem, we're going to place 100 grams at the 60. So instead of placing 200 at the 60, we're going to place 100. We set it up the same way. Torque is force times radius. Only this time our force is 100. Our radius, how far we are from the center, is still 10. That gives us a torque of 1,000. Now we want to figure out how far should we place a 200-gram mass on the left-hand side to balance that out. So the torques are the same. The torque on the left and right must be the same, so we have 1,000 for the torque on the left. We're always hanging a 200-gram mass on the left-hand side. And we're going to solve for the radius. So again, to get rid of this 200, since it's multiplied to our variable, we divide to get rid of it. Here the 200 cancels out. And we get a radius of 5. Now remember that this is not saying we're placing the 200 at the 5 centimeter mark. We're going to be 5 centimeters from the center. That means that we're going to place this 200 grams at the 45. That is 5 centimeters from the center. For the next one, we're going to place a 50-gram mass at the 90 centimeter mark. So again, the first step is to solve for the torque on the right-hand side. This time we're given a force of 50, and our radius is always the distance we are from the center, from the fulcrum. And this time we are 40 centimeters away. 10, 20, 30, 40. We get a torque of 2,000 on the right. We want to figure out how far should we place a 200-gram mass on this side to balance it all out. Now remember, the torques must be equal. So the torque on the right and the left must both be 2,000. We're always placing a 200-gram mass on the left-hand side. We're going to solve for the radius on the left. Because it is multiplied to our variable, we solve by dividing the 200. On the right-hand side, they cancel out. And we get a radius to be 10. Remember, that 10 is how far we are from the fulcrum, from the center. So we're going to place this 200 at the 40 centimeter mark, 10 centimeters from the center. For this last one, it says we have 100 grams at the 60 centimeter mark, plus another 50 grams at the 80 centimeter mark. So now what we have to do is we're going to solve for the torque. There's actually going to be two of them. We're first going to solve for the torque of the 100 grams. The distance of the 100 grams is, again, we are 10 centimeters from the center. That gives us a torque of 1,000. But then we also have to solve for the torque from the 50 grams and the distance of the 50 grams is 10, 20, 30. 30 centimeters away. This gives us a torque of 1,500. So on the right-hand side, we have a total amount of torque of 1,000 plus 1,500 or 2,500. We must balance that out on the left-hand side with a single 200-gram mass. So again, the torque on the left-hand side must also be 2,500. We're going to balance it out with a single 200-gram mass. Same as before, since we have our 200 multiplied to our variable, we solve by dividing by 200 on each side. And we get our radius comes out to be 12.5. Again, we're not placing it at the 12.5. What we are saying is that we need to be 12.5 centimeters from the center. This means we have to subtract 50 and the 12.5. We're going to place that at 37.5 centimeter mark. Now, on the back of this worksheet, we have some similar types of problems. Not quite as complicated, though, because we don't have to deal with the whole subtracting from the center, as you'll see later. So the second problem here, as a child, you used to ride a seesaw, still do perhaps. If your friend who happens to weigh 750 newtons is sitting 2.5 meters from the fulcrum, so 1, 2.5, how far from the fulcrum should you sit if you weigh 900 newtons? So we're going to solve this, and then we're going to draw ourselves on the seesaw. So we start the same way. We're going to solve for the torque, in this case, the torque on the left-hand side, because that's what we know. The force this time is 750. That is the force of the friend. And the radius is always the distance from the center, which is 1, 2.5. We are 2.5 meters away. This gives us a torque of 1,875. Therefore, we must have an equal amount of torque on the right-hand side. The torque on our side must also be 1,875. But our weight is 900. Since our variable is multiplied to the 900, to get rid of it, we must divide by 900 on each side. And we get that we should be 2.08 meters from the fulcrum. So we would say here we are 1, 2, and a little bit. We'll draw ourselves on the seesaw there. From that center. Now, this last problem, we have 2 people sitting on the seesaw. We need a third person to balance it out. So we have a 750 Newton dad who sits at one end of a 6-meter long seesaw, pivoted at the center. His 240 meter son sits at the other end. Where would his 650 Newton wife have to sit to balance the seesaw? So first thing we're going to do is we're going to solve for the torque of the dad. The dad has a force of 750 newtons. And we see that he sits 1, 2, 3 meters from the center. Remember, it is always the distance from the center that we need. This gives the dad a torque of 2,250 Newton meters. Next thing we're going to do is solve for the torque of the son. The son's force is 240 newtons, and he is also sitting 1, 2, 3 meters from the fulcrum, from the center. This gives him a torque of 720. Now what we see here is that we need more torque on this side. There's too much on the left, we need more torque on the right. And so that's where Mom comes in. Mom's going to have to make up the difference in torque. So how much extra torque do we need if the son already has 720? So 720 plus what? Equals the 2250 from Dad. And so we subtract the 2250 and the 720, and we get that Mom's torque must be 1530. Now Mom has a force of 650. And we're going to solve for her radius. Now again, since we have our variable multiplied to the 650, we must divide each side by 650. And we get that the radius comes out to be 2.4, which puts her about right here.